Hi. So what we used for the student cluster challenge this year was around the topics of, kind of useful computing and getting the most out of things. But firstly, we probably need to go back a little bit and have a look at what's been going on from this. So the student cluster challenge itself is based on, effectively, we had a challenge with 3 hours to analyze Lustre performance. We had 6 teams that will share their presentations of how they experienced that. Bear in mind that this is the first time that they've actually touched Lustre. They have 5 minutes to kind of go through this at a very high level, so it's kind of a whistle-stop tour of their experience. And what we'd like you to do as the audience is actually participate. So we'd like you to take part via Slido to vote for the presentations that you believe are the best. Okay, so the test bed that we ran for this, thanks to DDN, which were great with us, they obviously donated us an SFA 7990X. As part of that, we also had some hardware donated to us via Durham, who donated some compute to that challenge. The entirety of the challenge is based around a problem. So the problem obviously is that new applications need to operate on byte addressable ranges, and there's a big shift from sequential I/O to kind of random I/O, right? And we wanted to effectively prove performance in a repeatable manner. So the real problem is actually something that Hyperion Research pointed out probably May at ISC. And in May at ISC, they mentioned that HPC experts are an aging workforce. And we actually have a bunch of talent that is aging out. The problem with that is that we need to start getting the next generation of people on board, right? And there's also another concern is that users need major improvements in ease of use and ease of selection and ease of basically being able to optimize their environments. That kind of ties into what we talk about with benchmarks and tuning. And actually, we should be making benchmarks and tuning easier to execute. So the challenge was kind of split into two, and there's a lot of words here, but I won't go into too much of it. But we're talking about addressing the risk of skills aging out. And that means that we prove kind of productive computing by running and documenting extensively how that works. Each team ran a set of tests with some instructions to get them started, effectively running IOR and MD test. After that, they were asked to document extensively how they ran that, bit by bit. The idea is that each team should be able to pick up another team's results and execute it, because good benchmarking should be like good science. It should be repeatable. So, part 2 of the challenge, and that's currently going on right now, is that the teams have all got together and they have all effectively picked their own destiny by picking somebody else's benchmark documentation. And they're now executing the same information. They will get points for getting as close as possible to the original result. On top of that, what we've realized is that being able to execute things is great, but being able to articulate is more important as well. So we want people to be able to get up on stage and articulate what they mean by running benchmarks. And so part of the challenge is, and worth 25% of their benchmark results, that they can get up and articulate what's going on. So please vote for them. And with that, I will bring our first team, which is Strathclyde. Stand the microphone.
So start to the slide.
Switch slide, yeah.
All right. Hello, hi everyone. Our team is Strathclyde. We are from the University of Strathclyde. This is the first time we are from Glasgow, and this is the first time a Scottish team is participating in the challenge. My name is Mauro Arcidiacono, and my partner here is...
I'm Asa Hopkins. There's 3 more in our team who are doing the other part of the challenge right now. So that's Lewis, that's Wang, and that's Girish. So Girish, we only met today in person, and he's been... we didn't know if he was an AI until today. Sadly, he is not. An AI might help our performance. We also have sponsorship from Archie West, so that's the HPC cluster that Strathclyde hosts.
Yes, and we received some support from the Archie West manager, Richard, which actually helped us to be here and put the team together. So what did we learn in the challenge? So we learned the basic workings of a HPC distributed file system. We didn't know much about it before this experience. Actually, we learned quite a lot before the challenge and during it as well. We learned about input-output optimization, which matters a lot in HPC. And we now know that it can be quite challenging and very hard. It looks, sometimes you might think problems are easier than the way they look. We also learned that 4K is not a good choice for transfer size. We tried many times and, well, yeah, failed. Then to check the stripe size, that MD-test loves more threads, and that to properly tune Lustre, well, we didn't do well in this challenge, to be honest. That's why we did well in the others. This one was challenging for us, was very difficult for us, so we just made it a joke to call anyone but us.
I think it is a legitimate point. If you had, let's say, a leak in your bathroom, you wouldn't call a theoretical physicist from Scotland to come and fix it. So sometimes the best thing to do is to find the right person for the job. So the way that we tried to identify tunable parameters was essentially we spent most of our time trying to find what, the sort of best practice was for, setting default values before we actually look at, trying to profile it, trying to optimize it. Because some of the values, such as the transfer size, we picked terrible values to begin with, and we didn't really know what we were doing. So we found some advice online that said, you want transfer size to be a multiple of your stripe size. So we ran a command, found the stripe size, and picked a multiple of it. And that did help performance. Another thing we were told was to use one task per physical core of the machine, because this would alleviate memory bottlenecks. Now, of course, we didn't check if there were memory bottlenecks, but if it's best practice, we thought we might as well throw it in. We also changed the stripe, no, I think we were told the stripe count was 2, and changed the software to know that there were 2 stripes. We were recommended a profiling tool from multiple sources called Darshan, but sadly we ran out of time before we actually managed to do any profiling with it.
So some of the biggest challenges we faced were, first, we didn't pretty much know which were the reasonable defaults for many of the values to tune. We had some misunderstandings with the documentation. Actually, we thought that we were running simultaneously, but setting 2 parameters to 1, and well, it was serial after all. We had to change that. Then we couldn't use the intended block size of 32 gigabytes, and the time scaling isn't linear in block size. A 1 gigabyte run took 40 seconds, and an 8 gigs run timeout.
Right. So some of the parameters we did find that were good to tune was the block size, as we've already mentioned, the number of cores. So depending on the task, you either want as many cores as possible, or you only want 1 core per physical core, so no hyperthreading. Now, I think the best advice I can give is to pick the right team to do your competition. Because for the low price of a £5 Amazon voucher, you can get Eisenbards to run a programming challenge and get over 100% the performance we did.
So thank you very much.
So the next team up will be Scared to Compile.
Good afternoon. We are Scared to Compile. We're from Bath, and this is our presentation. So we learned why you perform I/O benchmarking because we were really new to this. We haven't done anything with benchmarking before. So we learned that optimization is a big part of why you perform I/O benchmarking. Since I/O operations can often be a significant source of performance degradation, you can find the bottlenecks of identifying and optimizing I/O bottlenecks is essential to achieving high performance in HPC systems. Resource planning is another big thing. So accurate benchmarking data can aid in resource planning by helping administrators understand the I/O requirements for different applications, which is crucial for allocating resources. And a big resource is the storage system evaluation. Since HPC environments can often use complex storage systems, including parallel file systems and distributed storage, I/O benchmarking can help in evaluating performance of these systems under realistic workloads and can make informed decisions. You can make informed decisions about the storage infrastructure.
Right. So what did we actually achieve? Unfortunately, unlike most of the other teams, we took quite a while to get started, mostly due to people struggling to log on, like you. And we only managed to do the sequential read and write tests. We didn't get to do the random input and output and the MD test. But what we did actually achieve, so after running the baseline tests with the write and read, the default settings for at least the read test weren't really accurate to what performance would be like in real life due to issues involving page caching. So one of the things we learned later on after running our final benchmark, so the initial kind of baseline test we got was, I think, around a block size of about 64 gigabytes. After running our final test, which was supposed to run about 5 minutes, which was about 512 gigabytes, we found that the read performance went way, way down. So we started off with like a kind of benchmark around 20 gigabytes per second, and that kind of dipped down more accurately towards a 6 gigabyte per second transfer at the end. So now we know that's because essentially we have to rely on the Linux part of the backend, basically. So some of the memory will be allocated to the application, some will be allocated to the cache, and if we allocate all of the memory to the application side of things, you don't get this kind of arbitrary performance from the application just reading straight out of the page cache. So that's one of the things we learned during the time. Of course, we learned how to use, we learned about the Lustre file system, but we also learned about Slurm for the first time. That was the first time we ever created a Slurm batch script. And yeah. So future improvement. What we actually learned during the final test or the final benchmark was that 2 of our cores seemed to be underperforming compared to the other 2. So we had like 8 tasks total for 4 nodes rather. And what we noticed was that 4 of the files were finishing a lot slower than the other 4. So we got suggested that CPU pinning might be a good idea, thanks to Chris. And yeah, so if we were to do this again, we'd infer more bottlenecks using some software implementations like Tau, basically to get a more visual understanding of what the bottlenecks within our system were. And also, if we had the time, we would create a more accurate benchmark. So there are applications which do want to use page caching. So you have things like Blast Informatics, where you want to read in the data first to create the data types, but then you want to load the data in again. So using an IOR script, you can kind of do that sequentially and, yeah, more accurately represent the task. Anyway, thank you very much for listening.
Thank you.
Yeah, you first.
Is it this one?
Try. Whoop, it works.
Got it. So we're Eisenbars, we're from Bristol, and this is our presentation. Chris has described our challenge already, so we don't need to expand it much, but we had to use IO and MD test to benchmark our file system, which is a Lustre file system. The problem was we knew nothing about IO. So after a bit of research, what is IO? Information transfer or accessing data. Read-write are often bottlenecks, especially if you still use mini disks, and they're often neglected. If you use parallelized application, it will be nice to also parallelize data access. But this is tricky. So we learned that Lustre is a parallel file system, and it meets these demands. So, yeah, our experience with Lustre was very daunting. We thought that the documentation was very extensive, but even the Lustre 101, when we went into it, it directed us to many resources, and we couldn't really find a very basic, from Lustre, a very basic explanation of what it is and all the basic concepts. We found most of it through national labs in the US, so NASA and Oak Ridge, who were very helpful. So that was our experience researching beforehand. And now I'll move on to the benchmark.
Yep, so the first benchmark we are asked to do is the IOR benchmark. That is for measuring the read speeds and the write speeds in the file system. It does that by writing some huge files of rubbish and testing how long it takes to write them, and then it then tries to read them and test how long it takes. Now, the first issue is that, in general, this will give you sort of the peak speeds. If you know the stored files are in a particular order, then when you try and read them, you maximize the bandwidth. That's not realistic for a lot of applications, which you need to read from random parts of the file system and need to sort of jump around in random locations. And so that's where random IO comes in. That will introduce sort of random offsets as it's writing and reading. And that'll obviously be a lot slower because it's not doing it all in order, but it'll be more realistic for certain applications. For the random IO, we found that the best way to tune it was to reduce the block size significantly, because since it's searching through the entire block before it reads or writes, if you reduce the search space just algorithmically, that'll be a lot faster. The next issue we had was cache effects. If you're testing a file system, often if you're sort of reading and writing, you can read directly from memory after you've written something. Alternatively, you can sort of queue everything in memory and then flush it out to write it all in one go. Those will give you artificially high results for your file system. You're not testing the IO, you're testing the memory bandwidth. So that's not useful. We need to make sure we avoid those cache effects. Two ways we found doing this. There are some parameters that ensure we bypass the IO buffers, and we read from a separate node to the one we read using a separate node to the one we used to write. Ensures we bypass the node's memory. And the other way of doing it is just setting the total data transferred by a node to be sort of at least twice its own memory, so it can't all fit in memory. It's definitely testing the storage system. Then in terms of tuning, in terms of tuning it, the first thing we found was the transfer size as sort of something we could try and make better. The total data transferred by a rank is called the block size, and we split it into IO requests of a specified transfer size. If it's smaller, you get more transfers per second, but fewer data for each transfer. If you send too many, wait, 1 minute in total?
Yeah.
If you send too many IO requests, you're slowing down the process. Bigger transfer size might overload it, so we plotted a graph and found the optimal of 32. The most important thing, though, was parallelism. If you have more nodes, you can obviously increase the total file speed, the file transfer speed, but you've got limited resources. So within one node, we tried to parallelize as much as possible without oversaturating it. And we found that having 4 tasks for each node would overload the IO, so it was maximally saturated at 2 ranks. That's something we'll come on to again in MD test, which doesn't fall prey to that same problem, because you can tune MD test using sort of -i, n, b, and also z, which isn't on there, because the way mdtest works is it will generate a tree of directories and populate it with files, and the time it takes to read those files, it measures the read speed for those files and also the metadata retrieval and the creation speed. So what you can do is you can create a bigger hierarchical data sort of file structure. Increasing Z gives it more levels, increasing B increases the branching at each level. And if you have enough files overall, then you fully saturate the I/O. Go nuts.
Okay, so we don't claim to know anything about Lustre, but we found out about striping, so we decided to tune this. We were using a client, so we can only change 2 parameters: stripe count, which is the number of OSTs, object stores target per file. I'm aware that there's also like file per process and stuff like that. So we were given 2 OSTs. We changed from 1 to 2, and also there's the stripe size, which is the size of the chunk per OST. And I think by default it is 4, but we found it was 1 megabyte, so megabytes? I don't know. So we changed it back to 4. We found out also things we should not do, which is stripe really tiny files, because that just adds overhead, but do stripe really large files at the order of 100 gigabytes. We shouldn't also overstripe because it doesn't lead to performance increase. Conclusions.
Well, the main conclusion is that theory will tell you quite a bit, but in terms of actually, it'll tell you there are optimal transfer sizes, there is an optimal amount of parallelism, but ultimately to find that optimal sort of point, it's just a question of trial and improvement. Parallelism we found to be really important, but also tuning each parameter will ensure that you're fully utilizing the resources that you've got.
So Lustre was very complicated. We did some stuff. We applied theory. We tried striping. No improvement. But we think it's because we only were given 2 OST and not really sure what kind of improvement we're expecting. Maybe it's to do with the setup of the benchmarks. It would be very nice to see it in practice, increasing performance. Thank you.
Next slide. And the next team is Bethel.
Hello, we're Bath Overflow. Funnily enough, we're also from Bath. Hopefully you'll get the pun. We were just told by Chris that being articulate is a part of this presentation, so hopefully that doesn't make us fail horribly, while the rest of our team downstairs is hopefully doing very well. Just for a little context, I'm a EEE student and I completed my placement in a data center. So I'd hoped that would give me a bit of an edge, especially because of the fact that I'd heard of Lustre before, but unfortunately I did not whatsoever. So also quickly apologize to the group of experts in the room while we say things that we just about understand. Like that. Yeah. So on to the challenge. So very quickly, during our challenge, we were missing 2 members out of 6, which is quite unfortunate. One was busy and the other doesn't exist because we only have 5 team members.
We've not heard from him since. Ironically, the one meant to present this is stuck in Wolverhampton, so
yeah,
it's a recurring theme.
So quickly onto the challenge. Lots of other teams have said lots of technical things, so hope that means we don't have to go into those details, which is good for us. But we had to. I didn't know that was there. That was a cheeky hidden meme. Okay, so we had to SSH into a head node and basically perform some Lustre benchmarks on 4 32-core dual proc systems. We effectively were just running some batch Slurm scripts, which ran an IOR batch file, where we pretty much, through quick deduction and frantic reading of documentation,
And random numbers.
And random numbers, we were changing these numbers in these scripts and the batch file and trying to get the best value possible. So Yeah, so some of the things we were doing here, we were adjusting the block size based off this derived equation here. I can't remember if we were told that or we calculated it. Hopefully we calculated it. Some things with the initial transfer sizes. So we initially used 64K, which is quite small, so it was taking way too long. We adjusted it to 1 meg to match the stripe size. We had an initial error where in our Slurm script, we're only setting 8 threads per node. We thought we were setting 8 threads per node, but we're actually doing 8 threads for 4 nodes. So we upped the number of threads, and that gave us a faster size. We maintained, part of our methodology was maintaining some constants so that we had some consistency so that we knew what we were changing was actually helping us or hindering us. And yes, we had our tests were meant to run over 300 seconds, which was to tell us that we'd actually done some decent throughput, but quite a lot of them were way too long or way too short due to some missing flags, so that took up quite a lot of our time.
And then we ran a random IO MS data test. There was initial, you can read it on the screen, but there was initial block size that was too fast. So they experimented it and found ones that were way too slow and ones that were not better.
Yeah, saying some things here again. We tried to increase some tasks for quicker reads. We faced some issues with that. We reduced the number of tasks to 16, so 4 threads per node, adjusted the block size for faster writes. We also tried to use Darshan. I had lots of trouble compiling it in the last 30 minutes from source. Some issues with the Linux path and all that, but I got it running and it spat out a bunch of errors, so that wasn't very helpful. But I was hoping that it would tell us exactly what we needed to change to get the absolute best, but in the last 30 minutes, but that did not happen. But at least I got
it compiled.
It compiled and put something out. Yes, we changed the number of tests. I don't know what that means. Sorry, I didn't write this. And then we changed the block size. We learned a little bit about Lustre in this challenge, but we also learned that we learned how much we didn't know just by only using it for 3 hours. But there's lots more to be learned, and thank you for listening.
Okay, so hello everyone. We are Team Cluster. My name is Arias.
My name is Sam.
And yeah, we're here to show us our analysis of Lustre file system. So without further ado, let's dig in. So of course, before doing any optimization, it's first nice to get a good baseline, and Sam will now tell us about that.
So we were on the screen, you can see some results from MD test. MD test is a benchmark that measures the metadata performance by creating and deleting large trees of directories and files in parallel. The results from this would be most important for applications that are writing many files in short periods of time. One example we gave was for web applications, which will be storing information about the state of the world for seconds, minutes, hours, and days every so often. But for us, we started by, our process was to first do it by hand, install our tools, do some configuration, do some testing, then work back through our steps to see what we did, and then write some scripts to automate the process. And the reason we did this was because we wanted to make sure our results are reproducible, that someone else can replicate our results. And it also makes it easier for us when we're making changes, because if we make one change and, this doesn't happen to make it better, in fact, makes performance worse, and we can go back and look at, okay, what do we change? And we can learn more about the system itself. So we first wrote a script to deal with the number of tasks. So we could do a run and quickly change the number of tasks that we're running with. Our motivation behind this was that we wanted to increase performance. However, we wanted to make sure that we weren't running into issues of I/O contention. We also configured, similar to other teams, we configured the block size to be proportional to the amount of memory based on the memory that a task will be using up as well. One thing was, as well, we made note of the transfer size. We didn't have too much time to experiment with this parameter, but we did get to try a few different values and analyze how it affects results too. We can move on to the next slide, or do you want to talk about it a bit more?
Sure, we can now talk about profiling.
So I was responsible for profiling. I was able to first compile the Darshan tool, which went quite smooth. The Darshan tool consists of two libraries. First is Darshan runtime, and second is Darshan util. The Darshan runtime library allows us to instrument MPI applications in two different ways. The first way was by compiling or creating compile time wrappers. And this allows us to compile a benchmark with the Darshan library as well. So when we run the benchmark, it is instrumented by default. The second of which is through library preloading, which allows us to dynamically attach Darshan to a pre-compiled binary. We took this approach even though we did compile the IOR and MD tests ourselves to experiment with compiler flags to see how they affect performance. Darshan provides us with information about the application's file access at the POSIX level, but it also provides MPI IO statistics. The Darshan utility library also provides you tools to analyze the output from the Darshan profiler. Most importantly, it gives us a utility to dump the binary output into human readable form, so I can actually read it. But more usefully, it also provides a tool to create a PDF report, which generates really nice plots that have nice, funny colors, and I can show to you on a screen.
Wonderful.
But we had enough time to create there's the Linux perf tool, which is coupled with the Linux kernel, which is a shame because I don't want to compile the Linux kernel. I would like to take a shallow clone. But we were able to build it and have a quick run of the tool as well. We can go on to tuning, or do you want to say anything more?
Yeah, I would just quickly like to note that the reason why metadata takes up such a large percentage of runtime here is because we were running on a relatively small block size, which meant that metadata actually was attributing quite a lot of computation time here. Now, moving on to tuning the striping configuration, here are the commands that we run and the variables that we were interested in. And with just by tuning all of these variables, by first of all enabling striping with the available OSTs on the system, which were two, we were able to get thereabouts 12% improvement from about 5.5 gigabytes to 6, and we're also able to look into other tuning parameters such as max RPCs in flight and 30 megabytes, which didn't actually impact performance for us since since every rank had was working on its own file. There was no communication involved, so MPI-IO wasn't part of this. As you could see also in this graph, there was no MPI-IO. And yeah, that's about it for that.
So on this final slide, we did so much, but one thing that we wanted to do if we did have a bit more time was to look at the number of processes and how it affects runtime. We do have a graph, which we can say that 4 is the number of processes you should use, but that's not good science, and we would like to have more time to investigate how this affects performance.
Exactly. And with that said, thank you so much for listening, and hopefully now we'll be able to use this knowledge to get better results.
Hello, everybody. So we are parallel pioneers from University of Bath. So I believe we might be the last student challenge to present.
I think so. So we'll try not to keep you from coffee any little bit longer. So we'll dive right into it.
Okay. So in our challenge, there's 4 of us working on it. 2 of us here and 2 downstairs. And I think basically we're rookies at this, so we just are about to tell you pretty much the same as every other presentation, but ours is red. Oh, thank you. Oh, there was more to it.
Oh, wrong way. Oh, thanks.
Anyway, yeah, there was more to it than that.
Sure.
Yeah.
So of course, for this competition, we just started out with there are 3 sections, but to be fairly honest, like other teams, who's kind of relieved to hear we weren't the only ones who were only able to finish the first section, which is comprised of the 3 different types of testing. So we'll just quickly run through that. The first one was just I think you missed go back to the first one. Sorry. Yeah, it's IO testing. Yes, sorry. So this is just the basic read and write one. So it's just us setting it up on the basic 4-node 8-thread cluster. We just got comfortable writing the batch files. After about 2 hours and 30 minutes, I think we got the hang of being able to configure the files and be able to write those and run the Slurm jobs comfortably. From then, we just started tinkering with the block size. I think we modified it all the way up to 512 gigabytes to satisfy the requirement of running for 300 seconds. And then from there, we just did the write one on top of that, following it using the existing test files that were written after the first write test, and then just running the same batch job over those. So we got, 699 megabytes per second. Looks pretty good, but wish we had more time to test it. So, oh well.
Yeah, same with the other challenges we did. We wished we had more time, but we learned a lot in all of them. The next thing we managed to do, we've gone the wrong way again. So the next thing we did was the random test. And so our configuration, we used the same as before, 4 nodes, 8 tasks, and we just copied and renamed the script and made some modifications which are there on the screen. And I think the block size is a lot smaller there than previously. And also we had to copy and rename the batch file. So this was all a learning experience for us, never using this before. And I think by this point it was already about 20 minutes to go when we had got to this point.
Oh, I think we got to the last MD test with 3 or 4 minutes to spare. So I'm really thrilled that we got this, and I'm incredibly proud of it. You should go to the last slide there.
I think I'm pressing it left. Here we go.
Yes, we got it this time. Okay, so we got this one done, I think, with the last few minutes we got there before. So we just tried to put it through, pass it so that we're trying to run on 16 different individual directories for each one. So multiply by the 8 tasks going, hopefully got 128. I think that got it right. It looked good when I ran it through there, so I think that hit it. So that was kind of a learning experience as well. We weren't really familiar with the idea of running a metadata tests. So I'm going to go to the conclusion if you want to.
So that was the last minute MD testing, and we're going to show you what we learned. So we need to pay attention to block sizes, and we did take a little bit of time to get started with this, and we needed to work out the differences between reading and writing our files. And there was a lot of information that we were given, and it took a little bit of time to get through it. So it was a steep learning curve, but we learned a lot on this, all of us.
Yeah. I guess one of the biggest takeaways for us was kind of just appreciating how different the reading, writing, and meta-different tests were and why you would differ them. I guess the analogy I kind of came away with this is kind of like a triathlon. You wouldn't just kind of do one, depending on the application, you wouldn't just commit to one sport. You try to get around it depending on what it is. But obviously, everyone's parallel tasks are going to vary. So being able to have a quick understanding of what your capabilities goes a long way.
Okay, I think that's it for us. So we are parallel pioneers from University of Bath. I was certainly a pioneer getting here. This is actually the first. We had 3 of us. 2 of us came from Bath, 3 trains. I came from Scotland, 3 trains, 1 cancelled, 2 delayed. So this is the first time that we've met each other in real life. All of the other times have just been online. So really excited to be here.
Yeah.
So
cool. Thank you.
Thank you.